The last section of chapter 1 that we're going to cover, 1.5, is on infinite limits and limits at infinity. But we're going to start this lesson, we're going to start by just reviewing essentially some things that we already know about vertical asymptotes and removable discontinuities. So that's where we're going to start. And then we'll get into some of the infinite limits as well. Okay, so think about things that we've already covered in this class and in other classes, but we've talked about these things in this class as well. So if you get, when you sub in a value, so you have a function that's an n of x over d of x, if when you sub in a point at x equals c, if you get a non-zero number over 0, so you spend a lot of your time in college algebra pre-calc finding vertical asymptotes by setting your denominator equal to 0. And in most of those times in like a pre-calc course, those values that you were getting weren't also making your numerator 0. You were getting just where your denominator alone went to 0. So when you get this non-zero number over 0, that's when you have a vertical asymptote. Okay, now when you get a 0 over 0, and we've seen some of this before, that is typically going to be a little hole, a little removable discontinuity at x equals c. The only thing I'll say is there is kind of this little cautionary note I have here in parentheses, which is technically, like in this example that I'm talking about here, if you had something like x minus 1 over x minus 1 squared, technically if you sub in 1, you get 0 over 0. But actually this one is a case where there's not a hole in the graph. Essentially, if you can reduce a common factor, which you can here, you can reduce one of the x minus 1s, and then you end up at 1 over x minus 1, this is actually a vertical asymptote and not a hole. So you really have to look at what happens. It's like after you reduce common factors, do you get a 0 over 0? That's kind of the question you have to look at. This doesn't happen all that often, honestly, that you'd have something like x minus 1 over x minus 1 squared and have to think about reducing it in order to get to this 1 over x minus 1, and then it's a vertical asymptote. So let's just kind of talk about the most common situations. So what are we talking about in our most common situations? When you get a number, a non-zero number over 0, that is typically going to be your vertical asymptote. And when you get a 0 over 0, this is typically going to be your little removable discontinuity. Again, this is kind of what happens. We have to have this little caveat, but this is most of the time going to be when you get your little hole in the graph there. Okay, let's look at just an example or maybe two. And this is, again, things that we've already talked about. So number 1, let's say I have f of x equal to a nice rational function here, x minus 3 over x squared minus x minus 6. So when we think about vertical asymptotes and removable discontinuities, we're looking for certainly places that make our denominator go to 0. So we would start off here and say, okay, this factors to x minus 3 and x minus 2. And so both of these are going to be values that make my denominator equal to 0. So I'm looking for where my denominator goes to 0. And so my denominator goes to 0 at x equals 3 and at x equals, oops, this was x plus 2. So at x equals 3 and x equals negative 2. Now, which situation do I have? So if we notice, if you sub in f of negative 2 into your original function, you would have negative 5, negative 2 minus 3, over 0. Non-zero number over 0. So this implies that x equals negative 2 is a vertical asymptote. So we knew that they were both discontinuities. So we knew we had a discontinuity at -2. What type? We sub it back in. It was non-zero number over 0. That's a vertical asymptote. All right, the other discontinuity is at x equals 3. What kind is it? Well, let's sub it back into the original function. And when we do that, we do see we have a 0 over 0. So we have the x minus 3, and it's just one factor of the 0 over 0. So it's not that special case I was talking about where you could, maybe have a little bit of a different thing happening there. So in this situation, what we end up with here is our removable discontinuity. So x equals 3 is a removable discontinuity. All right, so that's your most common situation there. Okay, let's look at another one, number 2. And suppose we were looking at a function, let's call it h of x, is equal to, and suppose we had 2x minus 3 times cotangent of 3x, let's say. All right, so we're looking for discontinuities, and then we'll decide if they're vertical asymptotes or just little removable discontinuities. And so 2x, there's nothing to worry about there. But of course, the cotangent of 3x, this guy I do need to worry about, because that's really cosine of 3x over sine of 3x. And I do need to be concerned about where that denominator, sine of 3x, is going to go to 0. So we did an example like this in the last section. We really want to think about this as, maybe initially thinking about, if I'm looking for where sine of 3x is equal to 0, let's initially just think about, well, where is, and then just use some other variable temporarily, where is sine of z equal to 0? So for what values of z is sine equal to 0? Well, sine's equal to 0 at 0 and pi, but that's just the fundamental period. Of course, we can keep adding increments of pi or subtracting, going in the negative rotation. And all of these are going to be values where sine is equal to 0. But z was really just a temporary way to think about this. Z is really equal to 3x. So I'm thinking about where 3x is equal to all of these values. And so what we do then is we solve for x by just dividing both sides of these, what really is representing many equations. And so we have x equals -2 pi over 3, negative pi over 3, 0, pi over 3, 2 pi over 3. And so, these go on and on in either direction. And so what do we really have here? And actually, it might have been easier to first represent, this is kind of another way to go. Maybe first think about representing z as any integer location of pi. So k pi, where k is any integer. That's what the z solution was. But again, if z is really equal to 3x, then we could maybe just think about this form and dividing both sides by 3. And so now what we get is that x is equal to any k pi over 3 again, where k is any integer. So these two, we have the expanded form versus kind of the condensed form. Now these are all places, sine and cosine of the same angle, cosine of 3x, sine of 3x, they're never equal to 0. Sine of theta, cosine of theta are never equal to 0 at the same location of theta. So this means all of these values, if we subbed all of these back in, so if you were to evaluate and sub back in h of any of these k pi over 3's, you're going to end up with obviously 2 times k pi over 3. That doesn't really matter. But essentially you're going to end up with a non-zero number over 0. So I don't think we really need to write all that out. That's kind of awkward. But essentially it's not going to be 0 over 0. These are going to be vertical asymptotes. And so that's really our final result here. So x equals, so we're going to have vertical asymptotes. So we have vertical asymptotes at x equals k pi over 3, where k is any integer. All right, so that's just a little review. Okay, so we've talked about these concepts before. Now what we want to go on to here is we want to start to talk about limits at, we're going to talk about infinite limits, and then also limits as x goes to plus or minus infinity. Here we're going to start off looking at some limits that are still limits as x approaches a constant, but they're going to involve limits at a location that might potentially be a vertical asymptote. So let's take a look at this graph and kind of recall that your limit question was always looking for, like, what is the real number that the y's are closing in on. So if we look at this first example here, it says, what is the limit of f of x as x is approaching -2 from the left? So as I am getting closer and closer, traveling along my function, approaching -2 from the left, right? So this is the idea. We're getting closer and closer to -2 from the left, but traveling along the function. Well, these values just continue to get bigger and bigger and bigger. And so we might say that these values are going to infinity. And it's okay to say that, but what we really want to realize that when we say that these values are going to infinity, we're really condensing in that statement that this is really saying that this limit actually does not exist because it is going to infinity. It's kind of packaged in that statement, is saying that this limit, as in this case, x approaches -2 from the left, it doesn't exist because it's going to infinity. All right, let's take a look at the limit as x approaches -2 from the right. So again, I'm thinking about values coming at -2 from the right, but traveling on the function. Right, so as I get closer and closer to -2 from the right, these values are going down to very large negative numbers. So these numbers, these values, this function is going to negative infinity. Now again, when we answer that, we're really packaging in this statement saying that this limit that we're looking at here actually doesn't exist. It's not going to a real number. There's no limiting value to this. This is just continuing to grow and grow, or decrease and decrease. So there's no limiting nature to this. And so we're really saying that the limit doesn't exist because it's going to negative infinity. So these infinite limits, these limits that equal one of these infinities, are happening at the occurrence of our vertical asymptote. So this infinite behavior is occurring where there's a vertical asymptote. So you can see that on your graph. And so that means that, and we kind of alluded to this before in a previous example, in a previous section, but when you evaluate a limit, when you get this non-zero number over 0, that is going to tell you that this limit is either going to be going to infinity or it's going to be going to negative infinity, because there's a vertical asymptote there. So because there's a vertical asymptote. So again, we're going back to our knowledge of even pre-calculus of realizing this behavior of getting this non-zero number over 0, and that meant there was a vertical asymptote. And now we're connecting, well, that means that my limit is either going to be going to infinity or negative infinity. Now, you're going to have to decide which, and there's a couple of different ways to do that. So in order to decide which of these it's going to, meaning is my limit going to infinity or is my limit going to negative infinity? So to decide which, there's kind of two different options here. I would say you can either kind of just take a look at the graph. So you can go to the graph if you're knowledgeable of the graph, or even with your graphing calculator. Or, and I'll be modeling both of these, you could use, and what I'm just going to kind of generically here call this approach signs. You can evaluate the signs of numbers that are maybe approaching -2 from the left or right, for example, and plug in some numbers that would be close. You already know your answer is infinity or negative infinity. You're just trying to figure out if it's positive or negative. So we'll look at both of those. So, one thing to kind of keep in mind here is that these are not, kind of what I was saying, this is not answering like the limit is equal to this real number. Infinity and negative infinity, they're not numbers. They're just expressing this unbounded either growth in the positive or in the negative direction. All right, so infinity is not a number. Another thing just to kind of be mindful of as we're going through here, don't confuse your non-zero number over 0 conclusion, meaning vertical asymptote, some sort of infinite answer, with what we did when we got 0 over 0. When we got 0 over 0, that meant it was indeterminate. The answer was not yet determined and we had to do some work to get there. So we can't forget what we know from before. So let's take a look at an example. Suppose I have g of x equal to x minus 1 over x squared minus 1. And we're going to just do a couple parts here. So suppose I wanted us to look at the limit as x approaches 1 from the left. So I want you to kind of just go back to the same line of thinking. Like, what do I do first? I think about direct substitution. The problem is here, I get 0 over 0. And so right away, I'm making you go back to what we've done before. That is our indeterminate form. And so we need to know that that means we need to do some algebra. And in this case, it's probably the most obvious algebra of, in that denominator, factoring into our difference of two squares. And that's going to allow us to do some reducing of x minus 1 over itself. And so, remember, the functions aren't equal after you reduce, but their limits are equal. So essentially, you had a little hole in the graph that you've now filled in. So you have changed what that function is, but that's okay because the limits are equal, and that tells us where that hole was. And so this limit now, I can reevaluate it with direct substitution, and I just get a half. And remember, left limit, right limit doesn't matter. If you can evaluate the overall limit, then it's the same approach in those kinds of situations. All right, so we're just being mindful we don't forget what we've learned before and when it's appropriate to do so. Now suppose I had been asked the limit as x approaches -1 from the right of, again, the same function, x minus 1 over x squared minus 1. So again, I would start by taking a direct substitution approach. -1 minus 1 would be -2 over -1 squared is 1, 1 minus 1 is 0. So where 0 over 0 was indeterminate, -2 over 0 is not indeterminate. This tells us something. I know by looking at this, my answer is going to be infinity or negative infinity, and we don't yet know which, but we know that when we get a non-zero number over 0, so when we see this, here's what we know. We know that we have a vertical asymptote at x equals -1. And that tells me that my limit as I approach -1 from the right is either going to be going to infinity or negative infinity. I don't know which yet. So to decide which, we're going to go to, there's two different approaches. It could either be looking at the graph or using signs of numbers to decide which. Okay, so that's what we're going to do now. So, oops. Okay, so let's say this. So, to decide if it's going to be infinity or if the limit is going to negative infinity, there are two different approaches that I would be okay with. So the first one is to look at the graph. And if you're not familiar with your graph and you just use your graphing calculator to look at the graph, that would be okay. But I would still want you to give me just a rough sketch of the graph, so I knew that you were looking at the right thing. So if we were to take a look at the graph of this function, so again, what do we know? We just said we know that there is a vertical asymptote at x equals -1. If you remember anything about your rational functions, the degree of the numerator is less than the degree of the denominator. So there's also a horizontal asymptote on the x-axis. If we wanted to plot some points, if you subbed in 2, you'd end up with 1, just to kind of have a point to plug in or so. So if you graph this on your calculator, you're going to see, and this is a rough sketch here, but you're going to see something kind of down in this region here. Again, you would actually have a horizontal asymptote here and here. And the other thing, just for completion's sake on my graph, remember from part A, we discovered that there was a 0 over 0, a little hole in the graph at x equals 1. So actually over here at x equals 1, and then up here at a half, there's a little hole in the graph. So this part of the graph is going to look something like this. Not that you'd be able to see that hole on your graphing calculator. But here's my rough sketch. So what am I looking at here? I'm looking at the limit as x is approaching -1 from the right. So I'm supposed to be traveling along my function, approaching, getting closer and closer to -1 coming from the right. So I can see that these values are going to positive infinity. They're getting bigger and bigger and bigger. So that would be one way to write your final answer, kind of using that graphical argument. The other kind of way to think about this is you've already decided that you know that your answer is either going to be infinity or negative infinity. You could just plug in some numbers that are really close, or a number that's really close to -1 from the right. So if you were to think about subbing in, so if you were to sub in, let's say x equals -9/10. So something approaching -1 from the right side or from the greater side. So if you were to do that in that original function, so if you were to do that, negative, so what am I subbing this into? I'm just kind of thinking about subbing this into my original function. So negative 9/10 minus 1 is negative 1.9, so you'd have a negative number divided by negative 9/10 squared would be 0.81, minus 1 would also be negative, and a negative divided by a negative is positive. And you already knew your answer was going to either be infinity or negative infinity, so now you've decided this is going to positive infinity, or again, you could just say infinity. So either of those would be valid techniques, I think, for deciding if it's going to infinity or negative infinity. All right, let's look at another example. So number 2, let's take a look at the limit as x is approaching pi over 2 from the left of secant of x. So this will just give us a chance to review. We haven't probably used secant or cosecant too terribly much. So we would start it with direct substitution, right? And we would think of secant as 1 over cosine, and we would sub in our pi over 2, but cosine at pi over 2 is 0. But I've just gotten a non-zero number over 0, so this tells me I have a vertical asymptote at x equals pi over 2, and this tells me that my limit then, so this means that my limit as x approaches pi over 2 from the left is either going to be infinity or negative infinity. So let's go to the graph to decide which. So let's go ahead and take a look at the graph in order to decide which it is. So in terms of work that I would want to see from you, I definitely want to see this result where you get a non-zero number over 0. I'd want you to tell me that means, vertical asymptote, and then maybe a quick sketch of the graph and then your final answer. That would be okay. But give me the part where you're observing that you get that non-zero number over 0. And then from there, it's kind of almost what we do in our head, realizing that means you're at either infinity or negative infinity. Okay, so let's take a look at just getting a little sketch of good old secant. So hopefully you remember when you first learned to graph secant and cosecant, you kind of use the graphs of their reciprocals, so cosine sort of as the structure in place. And so you kind of think about, okay, if I was to graph cosine, so the graph of cosine, might look something like this. If you think, obviously it keeps going, but, this is here at 2 pi, and here I am at pi. And this is at 3 pi over 2. And then here's where I'm really kind of interested in this one. Oops. This is where I'm at pi over 2, and obviously over here we're at negative pi over 2. All right, so this is my graph of cosine. This is just a little review for you for trig functions. So essentially when you take the reciprocal of cosine, it doesn't exist, and then that's where you would get your vertical asymptotes. So you have vertical asymptotes on your cosecant graph where the cosine graph had x-intercepts. And so then the actual graph of your function of secant, it was always kind of nice. You could almost think of, like, if I had to take a visual of what a reciprocal might look like, it's kind of flipping these curves out. That's not any precise math or anything, but kind of when you're learning it in trig, that can be helpful. So you get these like U-shaped curves that approach these vertical asymptotes. So these are your graphs then of your secant function. So I'm really looking at, this is our graph. So these are the graphs of secant. So what's in blue are the graphs of the secant curves. All right, so now we are approaching pi over 2 from the left. So as I am getting closer and closer to pi over 2 coming from the left side, or the smaller side, I can see these values going to infinity. So this tells me that my limit is going to be going to infinity. All right, one more, and then we'll end this video and come back next time. So I just want to also touch on our log function, because that's the other, we have several types of functions that have vertical asymptotes. Rational functions, things like polynomials over polynomials, where those denominators go to 0. Certainly trig functions, a lot of them have, again, non-zero numbers over 0. But the other one that we get a vertical asymptote with, and it's not because it's non-zero number over 0, it's just one of our properties of the natural log or any log function. So if you remember, first of all, if you tried to do this with direct substitution, you would get an error in your calculator, right? Because you would sub in, you would try to sub this in, and you would end up with, natural log of 0, which does not exist. So that's what you would kind of end up with here. But that is not going to necessarily mean that the limit doesn't exist. So what we're going to do here is we're going to go to the graph. All right, so our graph of our natural log function, so if you think about, kind of the basic shape of the original log function. So if you were just going to talk about natural log of x, it has an x-intercept at 1, and it also has a vertical asymptote at x equals 0. And so this is the basic shape of your natural log function. So it looks something roughly like this. And then the -2 here, that means that this is going to take my function, the -2 on the inside, and shift it to the right 2. So that's going to take every kind of key feature of this graph and move it right 2. So including the x-intercept, and then also including the vertical asymptote. So my vertical asymptote has now went right 2 as well. And now the same basic shape though on this graph. So this is, our graph of, so this is the natural log of x minus 2. Let me just label the one in gray, the lighter one here. This was natural log of x. All right, so if you think about your limit here, getting closer and closer to 2 from the right. So as I get and I approach 2 from the right, these values are going to negative infinity. So this one, it's not a 0 over 0 form, but it does require a little bit of knowledge that we have to kind of recall that there was a vertical asymptote on the natural log function. All right, so those are some examples where we end up with a limit that goes to infinity or negative infinity. So technically doesn't exist, but just has this unbounded behavior. So next time what we're going to come back and look at are going to be limits at infinity, meaning the limit as x goes to plus or minus infinity.